Our next topic is a discussion of directional derivatives. Now, what is a directional derivative? Well, let us go back to our discussions about the efforts we had to define a derivative for a function of two variables. So let me just mention that. In our efforts to define a derivative for a function of two variables, okay, we came across the following. Okay. We were unsuccessful since the limit p going to p0, f of p minus f of p0 divided by the length of p minus p0 did not exist for even very simple functions. So we decided p should go to p0 horizontally or vertically. Okay. That means we did the following. In plane, we have a p0. So we either looked at this, choose a p and moved it towards p0 horizontally, which gave us, because x is the only variable, this gave us del f del x. Or we made it move vertically, that's to say this way, which gave us del f del y. Okay. We consider these as the partial derivatives and so on. Well, what is special about these two straight lines? Well, they are horizontal and vertical, and they are the easiest ones. Now we know a lot about straight lines. Let us now consider an arbitrary line through p0. Say we have an arbitrary line. Now, what happens if p moves towards p0? Well, since we have a line L and we have a point p0 already, we need a direction vector, that is a vector parallel to L. So say this is such a vector v. It is parallel to L. Actually, the direction of v, whether it points this way or the other way, will be important, but we will come to that in a minute. Okay, so what happens then if p moves towards p0 but on L? Can we formulate that? Well, of course we can. Firstly, the geometry of the problem is the same as the case of horizontal or vertical approaches, because the picture is the same and the ideas are the same. So I will redraw it. We have a point p0 and, well, say we have some line L, and hence we have a VL, or just V, parallel to to the cell. Okay. At the top, we have a surface. Okay. And this gives us a curve here. Something like this. Now, let me use some color, it will be clearer. Actually, I'm looking at what happens on top of this line L vertically. So, I have a curve here, gamma, and I have a plane. This is, say, plane pi. Okay, and this is what happens on top of P0. Now we take a point in here. Okay, actually not P, let me put it down here, a P, and P will move. Well, let me take a P on this side. Move it towards P0. Note that at this point, even though we started with a surface in space, we are talking about the plane pi. Everything happens on pi because P is on pi, P0 is on pi, and so on. So, okay, redraw it. Once again, firstly, the x-axis is L in our case. We have a curve gamma, something perhaps like this. And somewhere here, we have P0. And somewhere here, we have P. And we have a vector parallel to L. So a horizontal vector here. Okay. Now, what happens if P moves towards P0? Okay, in the context of the ratio of the derivative. So, we look at the limit when P goes to P0, but on L. And we look at f of P minus f of P0 divided by the length of P minus P0. Now, everything is fine so far, but we are in a plane, let us use it. Firstly, okay, L is P0 plus TV. So, P minus P0 is T times V. Okay. Now, V is a vector in plane actually, because its Z value is 0. So I will show it, okay, by, well, ABC or V1, V2, okay, and 0, so I will just say it is V1, V2. Actually, here I should put 0 as well. Okay, so V is this vector. I will not need this 0. Anyway, so this says that we are evaluating the limit of f of, now P is x0 plus tv1. Sorry. And y0 plus tv2 minus f of x0, y0 divided by, this length is nothing but absolute P times the normal vector V. Okay. Now this very much looks like an one variable limit, and clearly P goes to P0 means, in this setting, T goes to 0. So we have here actually T is the variable and it goes to 0. Because we don't have the x and y of P anymore, we represented them by P0 plus TV4. Now, this ratio, of course, is nice, but we have the absolute value. And when we talk about limits in one variable, we don't have it. We just let t go to 0. So, in one variable derivatives, okay, we don't use absolute t, but just t. So, okay, let us define this, the definition. Okay. The directional derivative of f at p0 in the direction of v is the limit t going to 0 f of x0 plus t v1, y0 plus t v2, f of x0 y0 divided by length of v, of course. Okay. So this is our definition of the directional derivative, shown by dv of f at p0. Note that here we did not use L, because after all, p will move towards p0, okay, and we only need the difference. And the difference says that it is t times a constant, and so t, and that constant is the vector. So we don't care about the line much. It is the vector that we care. So that's why we have just v here and not the whole line. So according to this definition, we can now calculate directional derivatives. We will comment in a minute of what applications or consequences this definition has, or why we define such a thing in the first place. But before that, let us simplify it. Now dvf at p0, recall, is this limit. Okay. Now in this, let me write it maybe. T goes to p0, f of x0 plus t v1, y0 plus t v2, f of x0, y0 divided by t length of v. Here it's implicitly assumed, of course, that v is not the 0 vector. If it is, there's no point in all this derivative directly. There is no direction specified by it. So here, okay, the length of v is quite superfluous. We don't need it, and it's not important. V only shows a direction. And so we can try to put a unit vector instead of it. This we can do as follows. Say S is t times length v. Then, of course, this is S going to 0, because if t goes to 0, so does S. This is f of x0 plus t v1. Well, t is S divided by length v, so it is S v1 over length v, y0 plus S v2 over length v, minus f x0 y0 divided by S. Now, v, remember, is actually a vector in space, but its z coordinate is 0, so we actually is a vector in plane. So, since V is in xy plane, okay, we have here our alpha angle. So we can write V over length V as cosine alpha sine alpha in plane. So, okay, that is actually replacing V with a unit vector in the same direction. Okay. So the formulation becomes so if V is cosine alpha sine alpha, that is a unit vector, then dv f at p0 is just the limit t going to 0, f of x0 plus t cosine alpha, y0 plus t sine alpha, f of x0 y0 divided by t. So this is usually assumed to be a definition, but here remember V is unit vector. Or whatever V is, we put here cosine alpha sine alpha, which is V over W. Either way, we pass to a unit vector, and we have this simpler formulation. It's the same thing, of course, but it's a simpler formulation. Well, before we pass to examples, let us remark on something. Okay. Well, do these limits exist? Well, clearly, it depends on the function, it depends on the point, and so on. But we have, as usual, one very nice theorem. Namely, okay, if f is differentiable, differentiability again, then all directional derivatives exist. And dvf at p0 is nothing but the gradient of f at p0 dot the unit vector in the v direction. Okay. Here, let me emphasize that even though it's given in vector form and is valid in higher dimensions, here, since our f is from R2 into R, we are taking these in the domain of f. So this is cosine alpha sine alpha in plane, and this is f sub x, f sub y at p. Well, geometrically, this says that all directional derivatives are projections of the gradient vector onto the unit vectors u, which are in the direction of v. So this says that the gradient f has a very important position here. It's the basic vector, which determines all directional derivatives. They are just projections of it. Okay. Why is this true? This is because of the following. Let us look at the limit t going to 0 of f of x0 plus t cosine alpha, y0 plus t sine alpha, minus f of x0 y0 divided by t. Okay, here v is, or rather u is cosine alpha sine. I'm taking it a unit for simplicity. Now, by differentiability, in this limit, I can write, instead of this expression, f of x0 y0 plus f sub x x0 y0 dot, okay, the difference in x's, that is delta x. Well, this is my x, this is my x0, so this is my delta x. Let me point them out. This is my delta x, this is my delta y. So, I have here t cosine alpha plus f sub y times t sine alpha plus t cosine alpha epsilon 1 plus t sine alpha epsilon 2 functions. Now this is f of xy. I have minus f x0y divided by t. So this is the directional derivative expression. Now here, note that epsilon 1 and epsilon 2 are functions which go to 0 if delta x and delta y go to 0. Of course, these terms cancel out. And, okay, let me just write it again. T goes to 0. This is, of course, f sub x at p0 cosine alpha plus t's cancel, f sub y at p0 sine alpha plus, I divide by t's now, cosine alpha epsilon 1 plus sine alpha epsilon 2. And t goes to 0. Of course, what happens if t goes to 0? As t goes to 0, delta x, that's t cosine alpha, delta y, which is t sine alpha, go to 0. So epsilon 1, epsilon 2 go to 0. It means that this limit is, these cancel out. We have f sub x at p0, f sub y at p0, dot cosine alpha sine alpha. So this finishes the proof. Now, this of course says that if we have differentiability, we have very easy access to calculating directional derivatives. You just take the projection of the gradient in the direction of the vector. And that gives you the directional derivative. Okay. Right. Now we will pass to examples. Bir ara duralım burada.